Hello YouTube, Guanyin269 here. Now today I'm going to be giving you all a math tutorial. Yes, I know, that's a bit different from what I usually do, but I thought, well, I've got knowledge in here, let's get it out here. So, the tutorial is on derivatives in calculus. If you already know what a derivative is, or how to solve one, or both, then you might not need this video, unless you're looking for a refresher. However, if you are a little bit unenlightened, well, I'll do the best I can to put out the facts in a way that you'll be able to understand. No matter what kind of audience you are, I'll put it out in a nice viewer-friendly format that will walk you through step by step. Okay, let's begin. So, in order to describe what a derivative is, I must first describe a circumstance in which one might use a derivative. So you're on a train. The train is automatic. It has a map, and it follows that map through a route. However, it is not programmed to calculate for other objects being added to the map unless they've been updated from an external source. Which is why it knows not what to do when a landslide occurs. It falls with boulders incredibly large and blocks the path. The train keeps going. It accelerates, and it's going to hit the wall. But you're curious. You want to know how fast the train's going to be traveling when it hits the landslide. To solve this, you'd use a derivative. Now we get on to the fun stuff. Before I begin to say what a derivative is, let me start off by introducing two concepts: a secant line and a tangent line. Okay. Now, in order to understand a secant line, you need look no further than your standard velocity graphs. Velocity is distance over time. So if you were to draw a graph that would detect where you are and how much time has elapsed, you'd be able to determine the secant line just by using 2 points. So say after 3 seconds you find yourself 17 meters from your starting point. And after 8 seconds from from the second you left the station, you observe that you have traveled 30 meters. So now, how would you know your velocity over that time period? Right? It would tell you just how fast you've been traveling in average over that period. To do this, we can't just use the time and distance of the whole trip. We need an interval. And an interval is evaluated with a difference. Now, in algebra, which is what this is, difference is denoted by placing the delta symbol, which is simply a triangle, to the left of the variable or number you're trying to find the difference of. So if you wanted to find the difference between 2 points on the x-axis, then its result would be denoted as delta x. So let's find our delta x and delta y, shall we? Okay, so our time interval, we find delta x by subtracting the larger value, which is our second point of observation, by the small value, the first point of observation. Since time progresses in a straight line, it's all positive, so the one further along is when we subtract this one that's further back. Okay, so our second observation was made after 8 seconds. Our first observation was made after 3 seconds. That gives us a 5-second interval of observation. Now at distance, we traveled 30 meters at our second point of observation, and we traveled 17 meters at our first point of observation. 30 minus 17 is 13. I'm just enunciating the teen, so judging by the sound quality of this, you might not think it's 30, which would confuse the issue. So forgive me for doing it. So 13. Now 13 divided by 5, that gives us 2.6. So our velocity is 2.6 meters per second. And that gives us our value. That's our Saccart line. So on a curve, it would just simply be a line from one point to another. And then we just simply evaluate the slope of it. Alright, now a tangent line is a bit different. You don't have 2 points, you have 1. And the line is bounced on it so that that line, if you have a curve, that tangent line touches that point, and only that point, but does not touch any other part of the curve. Which means that that tangent line is aligned perfectly with the slope of that particular point. Except that doesn't make any sense, does it? What's the slope of the point? Delta x and delta y have been reduced to 0. You can't determine any slope of any sort. All you get is 0. So it's a dead end, isn't it? Wrong. That's where derivatives come in. For that, we use a fancy thing called limits. You may have heard of these in integrals, which I'll also do a video on when I get a bit more information on solving them. But actually, they're a lot like derivatives. But I'll explain that in another video. When I have another video, I'll place an annotation link for it somewhere on the screen. You'll know it when you see it. And if it's not here at the time I'm making this video, at the time you're watching this video, then I haven't made it yet, evidently. Anyway, onwards and upwards. So back to our original train. Original train example. Say the train is accelerating at a rate of, well, let's determine it by that function. Y equals x squared. So for every after 1 second, it's traveled 1 meter. After 2 seconds, it's traveled 4 meters. After 3 seconds, it's traveled 9 meters. No, damn it. Sorry, nerves. I have social anxiety, so I'm a little bit nervous about doing this. Please forgive me. So we get a square. Okay? The distance traveled is equal to the number of seconds elapsed squared. Right. So now that we have that function, if we can plot it on a graph, we get an exponential curve, as we'd expect. Now I want to find the slope. Because this thing is at a constant value, a constant predictable value, we can determine a formula that will give us the slope. It will give us a tangent line, the slope of the tangent line for any point. It remains constant the entire way. Now, I've used about all the picture examples I can give you, and I need your imagination for this. It's the tool you come equipped with. Now let's come with the tool God was equipped with. Oh, damn it. The tool God was equipped with. Maths. So, to do that, I'll just bring the camera over to my little tripod, which is placed in front of a nice piece of paper that actually shows you our calculations. So let me have a little... I should have adjusted this earlier. Okay, that's about as good as we're going to get. Yeah. Okay. So, we have a graph. Now the mathematical formula for determining a derivative is, make it so, derivative is equal, so hang on. First, the notation for derivative is, since we're doing, we'll denote the function f, so f prime, and prime denotes that it's a derivative, is equal to limit where delta x moves to 0, and it's f of x plus delta x minus f of x divided by delta x. That's complicated, right? Well, it's really not. Let's move the page up a little bit and we'll see how it works. So our function is, well, f is equal to x squared. So let's run the formula, shall we? We don't need to substitute values for the coefficients or anything, we can just determine it purely by knowing what the function is. Which means that now we take, so it's x plus delta x squared minus x squared divided by delta x. Okay, so now we have our formula. So let's move on to the next step, shall we? We'll expand the brackets, and we do that by doing this. Okay, so our new equation is, so it's x squared, and you know this if you know basic squaring bracket equations, but so we'll assume knowledge of this. If you don't know it, just look it up. If you're on YouTube, there's plenty of other videos. It's one of the reasons it's one of the ways I learned. So x squared plus 2x delta x plus delta x squared minus x squared from this part over here over delta x. Now we can see something cancelling out here. Minus x squared and our plus x squared, they cancel each other out, because if you add x squared to something and then subtract x squared from it, well, it's as if it never existed. So we can remove that, which means our next equation we've gotten is 2x delta x plus delta x squared. Now we can factor out delta x here, which means that we get 2x plus delta x multiplied by delta x. Sorry, I kind of left myself a lot of room there, but you can see the triangle, so you know it's delta x over delta x. Now, since you're multiplying by delta x and you're then dividing by delta x, they cancel each other out, so you get. It basically brings the whole thing to over 1, which we can now remove the denominator completely, which gives us 2x plus delta x. And since delta x is going to 0, that means that if it did reach 0, we know what it's going towards. It's going towards 2x. So our final derivative is 2x. So that's our derivative. We have now determined the slope, which means that on our graph, if we drew a graph, that means that the slope of the tangent would equal the second you're observing multiplied by 2, which means that at point 1, at the first second, the slope would be equal to 2. At time 2, the slope would be equal to 4, then 6, then 8, and it would keep going. So the slope increases, but we now have a formula, a function in its own right, that can determine that slope. Okay. Now we've cranked out the math, let's take our camera back to where it was before. So there you have it. Effectively, all you do is a simple sequence, a simple function, a simple equation that'll give you a derivative. You don't need to substitute values for the coefficients to make it work. All you need is the function that you're using. But that means that for our person in the train, it means that he'll know how fast it's traveling over a distance of time, he'll know where it is, he'll know how many seconds have elapsed, but he can get this, he can get his tangent line. He won't be able to get a secant line when everything's reduced to 0. He's simply measuring at a single instant. Not between two instants, but one single instant. If the train hit the wall 25 seconds after departure, and yes, I know that'll be a rather quick death, but okay, we'll make it a bit more reasonable. So it's been traveling for 5 minutes. That would be 60 times 5, that's 300 seconds. That means the